Hey, this is a short video that will list some of the steps to help you graph a rational function. So remember, rational functions were fractions of polynomials. And there's 5 good things that you should try to do in order to plot the graph. So maybe the first thing, find the zeros. Remember, those are the X-intercepts. The second thing, find the Y-intercept. And so also, as you can see, I've written in yellow, like, how do you actually do that? So maybe I should say, to find the zeros, that's when you set the numerator of your rational function equal to 0 and solve that thing back for x. To find the y-intercept, that's when you plug in x equals 0 and figure out what number you get. That's the y-coordinate of the y-intercept. So VA, remember, is vertical asymptotes. So to find those, you're going to set the denominator equal to 0 and then solve that for x. And those are the spots where your function is undefined. So those are points that are not in the domain. So that's where you get vertical asymptotes. So horizontal asymptotes, it's just kind of these 3 criteria to memorize. There's 3 things that happen. So you have a horizontal asymptote at y equals 0. That's the x-axis, by the way. Whenever the degree of the top is bigger than the degree of the bottom. Remember, the degree is the highest power of the variable that you see. You get no horizontal asymptote if the degree of the top is bigger than the degree of the bottom. So I think I said that right in the first one. Degree of the top smaller than degree of the bottom. That's part A. That's when you have y equals 0. Part B, degree of the top is bigger than degree of the bottom. That is when you have no horizontal asymptote. And then part C, what if the degree of the top is equal to the degree of the bottom? Then the horizontal asymptote is on the line y equals an over bm, where those 2 things are the leading coefficients in your top and bottom. And then find the slant asymptotes if there are any. And that'll only happen when you've got a rational function where the degree of the top is exactly 1 more than the degree of the bottom. So something like x squared plus 1 divided by x minus 2. The degree of the top is 2, the degree of the bottom is 1. That thing will have a slant asymptote. And how do you actually find it? You just do polynomial division, and the quotient that you get, y equals that quotient, should be the equation of the slant asymptote. Really, there's a step 6, which is to plot additional points if necessary. But let's see if we can use these steps to help us graph a few of these. So we're supposed to graph x minus 6 over x squared minus x minus 6. And what I've done is I've taken what I wrote on the previous page and just made it super duper tiny, just so we can kind of follow it as we go. So number 1, let's try to find the zeros, or the x-intercepts. And that's when you set the numerator equal to 0. So x minus 6 equals 0, so x equals 6. So that's where this function crosses the x-axis. The next thing that you do is find the y-intercept. And remember, that's when you plug in 0 for x. So we're going to put a 0 for all the x's I see. You should get minus 6 over minus 6, so 1. So the y-intercept then is 0, 1, that point. The next thing you might do is find the vertical asymptotes. That's number 3. And so to do that, remember, that's when you set the denominator equal to 0. So we're going to set x squared minus x minus 6 equal to 0. That thing factors as x minus 3, x plus 2 equals 0. So that tells you have vertical asymptote, when x is 3 and when x is negative 2. So those are 2 vertical lines. Those go through the x-axis at 3 and negative 2. Those are 2 vertical lines that the function does not ever cross, but the function gets very close to on either side of it. Number 4, find any horizontal asymptotes. And maybe what do we see? We see the degree of the top. The power on x up there is 1. The power on x down here is 2. So the degree of the top is smaller than the degree of the bottom. So y equals 0 should be the horizontal asymptote there. And finally, are there any slant asymptotes? That only happens when the degree of the top is 1 more than the degree of the bottom. That's not the case here, right? It's flipped. So what does that tell you? There's just no slant asymptote. So how would you get an idea what this function looks like? You probably start by plotting any x-intercepts, where the vertical asymptotes are, and maybe where the y-intercept is, and then try to fill in from there. So the red, those are the vertical asymptotes that we got at negative 2 and 3. And then I know that this is the only spot that I should ever go through at 6 right here. That's the only spot you should ever go through the x-axis. And so what you might do, what's one other thing that I know? I know that I have a horizontal asymptote at y equals 0. That's telling me about the fact that the graph eventually, really far to the left and really far to the right, wants to kind of hug the x-axis. That's the line y equals 0. So how do you know whether you're above or below and what it's doing? Well, remember that your function wants to get really close to the asymptote on either side. And so that explains some of this behavior. What you might do too is pick a point over here, like negative 3 is a good x value that's like right here, say. If you plug in negative 3, you'd get a negative number. And what that tells me is that the function should shoot down this way and not up this way. Similarly over here, you see that I know that I'm never allowed to go through the x-axis again since it only goes through right there. So that's how I know that it's got to shoot up to the left and it's got to shoot up this way, right? Otherwise, it would shoot down, but you'd cross the x-axis again, and that can't happen if this is the only x-intercept. And then similarly over here, I know that I cross the x-axis right there maybe, and eventually though, it should hug the x-axis as you go really far to the right. So this is just kind of an idea of what the graph basically looks like. Let's try and do another example. So we're going to graph 3x squared plus 2 divided by 2x squared minus 8x. So I've done the same thing where I've tried to just write this kind of tiny, and we'll just do each piece one at a time. So to find the zeros, again, set the numerator equal to 0. When you do that, you would get x squared as negative 2/3. And when you take the square root of that, you get a complex number, right? You get a square root of negative 2/3, and that's not good. So it's not real. And so what's that mean? It means that thing never goes through the x-axis, so no x-intercepts or no zeros. Next thing we'll do is we'll compute the y-intercept. Remember, you're just going to plug in 0 for the x's that you see. So all these x's become 0. And well, you get 0 in the denominator then. Remember, it's never allowed to divide by 0. So that's undefined. And so what does that mean? That just means this thing doesn't have a y-intercept. That's all. Maybe to remind you about fractions, 0 in the numerator is fine. It's just 0. 0 divided by 7, 0. Cool. 2 divided by 0 though, not defined. So 0 is never allowed to be downstairs. Continuing, number 3, find any vertical asymptotes. And so remember, you just set the denominator equal to 0 and solve that. I think you can factor a 2x out of both of those. And so the 2x equals 0 tells you x is 0. And then set x minus 4 equal to 0 and you get x is 4. So those are the equations of your two vertical asymptotes. So this is the y-axis, that's a vertical asymptote, and this is the vertical line that goes through the x-axis at 4. So those are two lines that the graph of f here is never allowed to cross. Let's find some horizontal asymptotes. And maybe what do we notice? Well, the degree of the top is 2 and the degree of the bottom is 2. They're the same. So what we're using then is part C of our little cheat sheet for how do you find horizontal asymptotes. And part C says the equation should be y equals the leading coefficient of the top divided by the leading coefficient of the bottom. Leading coefficient of the top is 3, just the number attached to the highest power of x you see. And the leading coefficient of the bottom is 2. That's the number attached to the highest power of x you see. Therefore, the equation of the horizontal asymptote is 3 over 2, or y equals 3 over 2 to be more exact. Finally, what you check for is, are there any slant asymptotes? And there is not any, because, again, the degree of the top would have to be exactly 1 more than the degree of the bottom. So if that was a cubed up there, what I've highlighted, then you would have a slant asymptote. Since that's not the case, none. So what we'll try to do is put all this information together again. And this one's a little bit harder to do. You don't have much of a foothold with either of these to plot some points down, but you can plot these horizontal asymptotes here. I'm sorry, vertical asymptotes. Yeah, V is for vertical, not for horizontal. Why can't I remember that? And then we could try to plot this horizontal asymptote here. And if we do, those are the red lines that you see. And I can plot this one as well. And then what we might do as well is use some of this knowledge that I know that when I draw this thing, it can't be down here because it's not allowed to cross to the x-axis here. And so what you might do again is you might plug in a point, like over here, this point maybe is -1. If you got a positive number, well then that would mean that your piece of your function would have to go up this way when it gets close to that vertical asymptote. And I know that really far to the left, the graph always wants to hug, and really far to the right for that matter too, the graph wants to get really, really close to that dotted horizontal line, y equals 3/2. So how are we getting these pieces again? Maybe we're using some facts that I know for this one. It never goes through the y-axis and it never crosses the x-axis. That's how I can kind of figure out where some of these pieces go. And by plugging in some test points and knowing, how does a function behave near an asymptote.